All right, so in this video lesson, let's have a look and let's learn about piecewise function. Okay, so this particular topic, in my teaching experience, I found that this is usually being embedded or being written as a subtopic in a section of a textbook, of any standard textbooks out there. But in my teaching experience, I have seen a lot of students struggling specifically with this kind of function right here, where it's called piecewise function. So I decided to teach this as a separate lesson on its own right here. And so think about, if this was my own textbook, then this topic, to me, it should deserve its own section in a textbook. Okay, and so in order to learn well with this particular topic, it is required that you must have learned about what a function is and how a function has a graph. Okay, so those two important topics must be required. So you got to know what a function is and functional notation. Okay, and then you have to also be aware that any function can be represented by a graph. So you have seen the graphs of some basic functions. Okay, and so now let's dive to it. And so do not be too worried about what a piecewise function is yet. Okay, and because I will get into that, and we will get to that explanation from the very ground and up. Okay, so now I'm gonna erase the title. All right, so now in our understanding about function, a function is a rule. Okay, a function is a rule that brings an input to an output, brings an input value to an output value. So it's a rule. Most essentially, it's a rule. And then at the end, we have, on top of everything, we have a strict requirement that for every one input, that rule can only come out with exactly one and only one output. Okay, so that's a recall about what a function is in my style of teaching. So at this point, let me come up with the following rule. So I'm going to define. So I am going to start out by introducing a function as following. We're going to define a function f of x. Okay, so just that standard notation, just that ordinary notation. Here's the function name. It takes x, okay, as the input. So this is the notation. And then the equal sign here is getting it ready for us to see the rule. Okay, so now I'm going to do the following. All right, I'm going to open, and so this is usually the way how it's written. I'm going to open a vertical curly brackets here, curly braces here. So I'm going to write down something as following. Okay, so there's a 3x minus 6. Okay, and then with a comma. Now, formally, this is, many textbooks says if x is less than or equal 5. Okay, but then for shorthand writing, usually that term here is skipped. Okay, and then on the other hand, there's another line down below here says 1/2 x plus 3. Okay, and with a comma. All right, and then if, but usually this can be skipped, x is greater than 5. All right, so ladies and gentlemen, this is your first piecewise function. All right, but so we call it a piecewise function. But why do we call it that way? Why do we call it that way? So as I go along, as we progress along with this lesson, you will understand the reason why it's called a piecewise function. Okay, but let's try to understand. At first thing, let's try to understand, instead of worrying about why it's called piecewise or what exactly that is. Well, let's try to understand what this rule is telling us, what this rule is communicating with us. Okay, so when you're reading a function in standard notation, here's what it says here. Now, at least for this rule, here's the rule. It's not only one rule. Okay, this function has two separate rules. Okay, this function has two separate rules. This function f of x, for any input, so this part right here, after the comma, I refer to this part in my teaching experience, I've always been referring to my students when it's face to face. I've always been referring to my students that this part right here is called the requirements. Okay, the requirements, or alternatively, we can think of that as a condition. Okay, so here's the thing: when you so at this point, provided that, or assuming that anyone has been fluent with the idea of taking an input and substitute that into your function, then if x equals 1, for example, if x equals 1, okay, if x equals 1, now we can treat x here as an input, okay, and so if x equals 1, so now I'm going to look it up. I'm going to look it up among the two rows. So really, the function cannot be two rows at a time. But the idea now is that depending on where or which input you are picking, it will fall into one of the two requirements here. So now I picked x equals 1. So I'm looking it up. And x equals 1 comparing with the two requirements. So it's stated clearly over here. X is less than or equal to 5. And then the other requirement is x is greater than 5. That is our indication. Okay? And so now if x equals 1, our value, our input here is less than or equals 5. Clearly, it's the one we chose independently. But now in this way, how our function is ruling it, in the way how our function is setting out the rule. Okay? In the way how our function is setting out a rule, then this rule, the function will be this rule. That's another way of seeing it, of understanding it. The function will equal or will be calculated using this rule. Anytime we're choosing an input x less than or equal 5. Okay? So in this case specifically, since I made that call, I called that, hey, let's pick input x equals 1. Okay? Then that means that now leads to saying that f of 1, okay, will equal. Okay? So now clearly the indication is so clear at this point. We have to pick that rule right there. This rule under this requirement or under this condition. And that's why I've been explaining that this part right here, where it has some indication, some specification that when x is less than or equal to 5, we use that rule. I call it, it's a condition or it's a requirement. We go with this rule under that requirement that x is less than or equal to 5. Okay? And so now clearly with the x that we independently chose, so f of 1 right here, okay, equals, so now the rule for this specific condition is that we go with that rule. Okay, 3 times 1, the input, minus 6. All right, and so, yes, in my role here being the instructor, I have to take it really slow, step by step, but now once you get the idea and keep it as simple as you can, then things will move on a lot faster than how I progress in here. And things in your own pace should be a lot faster than how I proceed here. Okay, so now 3 times 1, minus 6. So the rule is stated clearly, so now our final answer here is going to be a minus 3. Okay, because simply now 3 times 6, okay, order of operations comes first, so 3 times 1, that gives me a positive 3, minus 6 gives us a negative 3. That's the idea of how this rule works, and let's not be too worried at this point about the naming. Okay, so I just simply see this as a rule, and hey, it's a function. The reason I can say it's a function now because so far one input substituted in the function and we only get one output. Okay, and so nothing violated with the everything that we've learned about function. It's a rule. It takes an input and bring it out to an output. Okay, it brings an input to an output. Okay, and then that rule right here only come out with exactly one output and only one output, okay, for each input that I'm putting in. All right, so let's try again, shall we? So in this case, I'm going to erase this. So what if we go with x equals 10? We have our independence. I mean, we have our right to choose any values for the inputs we want because, again, the input variable in our function is regarded as the independent input, okay, the independent variable. So we can pick any value for that variable that we desire, okay? So now I've made that call, x equals 10 is about to be substituted into the function. So I'm about to calculate or evaluate f of 10. Okay. So now we're going to start looking for the rule to calculate f of 10. But now, since the input here is stated to be equal 10, now that means we're going to have to look it up. And now the rule says when we're using an input, it's indicated here clearly that if we're picking an input, if we have chosen an input that's greater than 5, this input is currently greater than 5. So when we switch to an input like this, we can no longer use the earlier requirements. I mean, we can no longer use the other rule over here, because this rule is only to be used when x, the input, was less than or equal 5. But now we chose a different input. And so this input here is clearly above 5 or greater than 5. So in that way, we are required to use this particular rule over here. So we switch to different rules depending on which condition that is. Okay, depending on the condition that we're doing. All right, and so now this means for this rule over here. So when x equals 10, greater than 5, we go with that rule. So the rule is saying that we multiply 1/2 with the input, and we add 3. Okay, so 1/2 times 10, okay, and plus 3, so that makes 5, and plus 3, our output is 8. And so again, let's double check. One input came out according to this rule. Now that we switched to a different rule, came out being 8, but exactly one and only one output on that particular input only. So far things seems to move like the way how a function is required to be. Okay, that meets all the requirements of a function. All right, and so that's the idea of how this kind of function works, how this rule works. Okay, this rule works. This one, I so-called for now, this one function has more than one rules for us to calculate the outputs. But we use only one rule at a time. And using whichever rule depends on where or which inputs that we have selected. If our input falls into this zone, this requirement, this condition, then we're going to have to use that rule to determine our outputs. Otherwise, if it falls into the other one, right, then we're going to have to use this different rule. All right, so each one of these is a rule, but one function can be switched to different rules. So the idea is that we're not using all of these two rules at a time, but we switch to a rule to a different rule to a different rules depending on where we choose our input. Okay, and so now, ladies and gentlemen, each one of these rules right here, we can see each one of these rules here as a piece. So one function, but it can be equal to separate rules, can be equal to multiple rules. So each one of these rules here is called a piece. All right, and so one function here, in other words, can be equal to different pieces of rule. And that's the reason why this kind of function is regarded as, that's why this function here is regarded as a piecewise function. Okay, piecewise function. It's really one word, piecewise. Okay, because it's containing multiple pieces. Okay, there are multiple pieces being involved in a function, and then it's a piecewise. It's to indicate us that sense about we don't throw in all pieces at the same time. We don't use all pieces at the same time. At the same time, we only use a piece or a different piece, or we switch to a different piece depending on where or which input that we have chosen, and that's why it's called piecewise. Okay, it depends on the idea. It depends on which piece that we're doing, and we switch to different pieces at a time. All right, and so welcome aboard. This is the idea about what a piecewise function is. Now let me tell you, this idea about piecewise function at this point actually is not new to anybody. You have seen it before, but prior to a formal learning about what a piecewise function is, then maybe instructors, including me, feel hesitated to mention that. But now let me show you what I meant earlier by you have seen this before. I'm going to switch over to my other board. All right, let's look at this function, and anyone know it. Anyone will know this function. f of x equals absolute value of x. F of x equals absolute value of x. But now, so indeed, this function belongs to, at least for the class here that we call, for the viewers who learn from this video lesson, for the viewers who learn class from me here, this course is called a pre-calculus course. And so in an earlier lesson, I must have introduced what's so-called the toolkit function. This function here is one among the toolkit functions. Okay, or many textbooks also refer to these toolkit functions as common functions or basic functions. Those are the kind of function that you need to know them anywhere, at any place, and we can use them at a lot of places. But this function here, now if we're having a look a little more carefully, the absolute value of x itself right here, we've learned from our previous course, we learned from our prerequisite course that absolute value of x on its own. So absolute value of x generally is the rule for this function. But to really tear it down algebraically, here's what we have learned from a course prior to this course right here. Absolute value of x will equal x. This, whatever that is, will equal to simply x if x is greater than or equal to 0. Okay, if x is greater than or equal to 0. So there you go, that absolute value of x for anyone from start, okay, and blending that with our current topic that we're looking at right now, piecewise function, then this absolute value of x equals to, on one hand, on one piece, equal to this piece if we have chosen an input value that's greater than or equal to 0. Okay, that's to tear it down real clear and real precise. And then on the other hand, this absolute value of x will equal minus x. It will equal to the opposite of the inputs we have chosen. Okay, that's what the minus sign is for. The opposite of the input. So the input itself can be whatever. An input is just simply a positive input, negative input, a zero input. Okay, but then if we have chosen a negative input, then the outcome, the final output, has to be the opposite of the chosen input. Okay, and that is the reason why now, that's what I said earlier, we have seen this prior to discussing about piecewise function. And so now if we're looking back at this absolute value function, it is on its own a piecewise function. So how have we been operating with that, and now how will we operate with this? See, f of 1. The input chosen here is 1. Okay, that means now x equals 1 is clearly a value above 0 or greater than 0. So that means we are going to follow with this piece right here. So f of 1 means, we're going to just equal 1. Because the rule says when input is, if we're treating this function here as a piecewise function, then the rule says if the input here is a value non-negative greater than or equals 0, then we're going to use that rule. So 1, the outcome equals exactly 1. The output equals exactly 1. But now the same function here, if I choose independently negative 5. If I chose so, negative 5. The input this time, I'm saying it out loud, is negative value. Negative value. Okay, and so negative value in this rule over here, the indication is clear. If we have selected an input being negative or a negative input, then we have to, the rule says we're going to have to take the opposite of the inputs to be the output. So in that way, well, negative 5, that's the input, but we have to take the opposite of that. All right, and so that's how it's been working the whole time so far. Okay, and so this is the way to understand absolute value a little more mature right here. Okay, because maybe you have seen this before, but of course it's very understandable that your professors back then, when in a course prior to this, we'll have a huge challenge to explain this, because it's quite challenging to understand as well. Okay, for any algebra students prior to pre-calculus, because your mind at that time, you're learning, your mind, that's your capability of learning, your majority in math is not far enough. Okay, has not been grown far enough for accepting this, for seeing this, philosophy, right, this fundamental. But now, as you have grown at this level of a pre-calculus course, that when you have grown far enough, then simply an absolute value is or can be understood legally as a piecewise function. Otherwise, prior to this course, professors back then might have just simply explained that, hey, anytime you give it, but see, the word is saying anytime you give it negative inputs, the answer is positive. Okay, that means we take the opposites of the negative inputs. So in this case, it's a positive. Isn't that how it's all consistent with what you have been learning? But it's, like I said again, it's very understandable that in case your professors in a course prior to this did not explain this way, because back at that time when your mathematical mind wasn't so mature, then it was really a challenging thing to understand this. At least that's what I see in my teaching experience. Okay. And so now we are reinvestigating the whole absolute value function as a piecewise function. So I'm not just saying again that piecewise function is not new to us. It's just things we have seen, but now we formalize that into a concept. Yeah. Okay. All right. And so now back to this function that I brought in. So if we chose, and now let me clean it up a little bit. So like I said, the term if right here is optional. Okay. Usually it's written on standard just like that. We write down the specific rules like that. And I also need to clarify. It's just a clarification. In this particular little demonstration example I brought up right here, there are only two pieces. One function equal to two pieces, depending on which input that we chose. But it should not be limited to only two pieces. I have worked with and I have seen piecewise functions that contain up to 5 or 6 pieces, or even more. And as you grow more mature in mathematics, right there, and apply your mathematics into different career fields that involve a lot of math, you will see the kind of piecewise functions out there where it may be divided up to 10 pieces or even more. Okay? But now back to this function. What about, because earlier I was trying the input being less than 5, and I was trying an input that's greater than 5, and we had a clear indication. So this one can also be tricky for somebody. What if we choose x equals exactly 5? What if we choose x equals exactly 5 in this case? Okay, then f of 5, but that means, see, we have chosen f equals exactly 5. So do we have an indication for which rule to use among these two when x equals specifically 5? That rule is here. Okay, well, this inequality reach x is less than or equals 5. That means we can use this rule for x up to, at most, x equals 5. So anywhere less than 5 and equals 5, it's under this requirement right there. All right, and so now I have a clear indication. It's now 3 times 5 minus 6. Okay, so that makes it 15. Okay, minus 6. So our final output is 9. And again, so far, at least on this problem right here, I've tried 3 separate inputs, and each one of them only came out with exactly 1 and only 1 output. So in the end, what I have here is a function, and it can be done through multiple pieces, and that's why we regard to that as a piecewise function. Okay, and so right in that way. Now we are ready for our first example, and the first example is just to get to know the function and be ready to be able to operate with these functions here fluently. So mainly just learn how to evaluate a value, okay, or a piecewise function at a specific given input. Okay, so here we go. Example 1. Now with example 1 we are given. Okay, and so now let's look at f of x. Okay, let's look at f of x equals, so here's I'll just give one function here first. So 2x minus 5 for x is less than or equals to negative 1, and then it equals to 4 for x anywhere above negative 1 but less than or equals 3. Okay, and then this is going to be x squared for x is greater than minus 3. All right, so in this example 1, we are given a piecewise function that has 3 separate pieces. And like I said earlier, it could be even more. Okay, but here, throughout the lecture, for simplicity, I'll just stay with 3 at being the most. Okay, but as far as being a piecewise function, you can have up to a lot of pieces. Okay, so now 3 separate pieces. Let's read to understand that a little bit before we advance on to the actual worded instruction of the problem right here. But see, this function will be the output of this function will be evaluated based on this rule. If we're giving in an input that's less than or equals negative 1. Okay, and then when we switch to an input that's anywhere greater than negative 1 and less than or equals 3, okay, then the function output will be determined by this rule right here, this particular rule. Okay, then we no longer use that one when the input is greater than negative 1 but still less than or equal to negative 3. And then we're going to switch to that third rule, that same function, but we're going to determine the output using that third rule if our x input is chosen to be anywhere greater than negative 3. Okay, and so that's the idea. And so now, simple enough, we're going to be looking at evaluate. All right, so we're evaluating. So how about part A? Okay, f of minus 5. Okay, so minus 5 here, we look right into the input. The input itself is being less than negative 1. Anyone at this point doing this kind of math problem is having a clear sense that negative 5 is less than negative 1. Okay, and so that means that we must stay with that rule over here. So the rule here for that says 2 times negative 5 and minus 5. Okay, and then order of operations now is making me to multiply these two first. So that gives negative 10 and minus 5, so it's negative 15. And so far, one input comes out with exactly 1 and only 1 output. Okay, all right. Part B. We want to evaluate again. But what about f of 2? Okay, f of 2. Okay, and so with f of 2, what are we looking at here? The input equals 2. The input equals 2, so that means now input equals 2 means we are no longer looking at this interval of values anymore, this zone of values anymore. So we can no longer use this rule. But now among these 3 zones right here, which zone here has our input value? Our input value is indeed in this middle zone right here, anywhere greater than negative 1 but less than or equals 3. Okay, and so our input is included here. That means we have to use that rule over here to determine the output. But this rule here is simply just a constant rule. That means regardless of whichever input that we are using in this interval, the output for our function is going to be 4 constantly. Okay, so it's 4. All right, so how about another try right here? Question C. I can create this as an FYT. Okay, an FYT means for your own trying. I won't give too much explanation, but I can just simply write down the final answer. But how about f of 2.5? Okay, and then you can now go ahead and search for the correct rule to use. All right, so after a little try, and hopefully you pause the video to leave yourself enough time like that, but also hopefully it didn't take too much time of yours. The answer for this is 4. Again. All right, and so now let's look at part D of the example. So on this space right here, let me continue with part D of the example. So what about we want to evaluate f at 3. F at 3. So the inputs, so that's in the note right here, the input x equals 3. But x equals 3, so let's look at the 3 requirements, the 3 conditions. Which one is including this input right here? Which one of the 3 conditions include the inputs x equals 3? This one right here says x is less than or equals -1. So 3 is not in this zone right here. Okay? This one right here say x is strictly greater than -3. So are we including -3 in here? Nope. I mean, it's 3. Okay? It's a typo there. So now x is greater than 3. Okay? I should have caught that typo from earlier. But so 3 is not included in this zone. So in other words, 3 is included right here. Okay? So 3 is included right here. And as a matter of fact, this inequality reads x can equal to 3 right there. All right, so in that way, we're going to have to use that rule again for evaluating the output of our current function. Okay, so now our final output is 4, needless to say. And again, one input is that one input and determines exactly and only one output. Okay, and so now what about question E right here? So now let's look at f of 4. All right, so now with f of 4, see what we notice? We change to an input being 4. Okay, so x equals 4. So x equals 4. For this input, it belongs to this piece right here. The piece where I just made that correction earlier, I mistakenly put a negative sign right here, but that was not meant to be there. Okay, so anytime that we chose an input greater than 3, which is 4 is obviously greater than 3 in this case. Okay, then now we have to go with that rule to determine our final output. All right, so now we're gonna have to be doing. The rule says in this condition, the rule says we have to square that input. And that gives me 16. All right, and that is our input for that. I mean that it is our final output for that. And once again, one input determine exactly one and only one output. All right, and so example 1 gave us a clear sense about how we operate and how we evaluate a piecewise function at various different values, at various different input values. Okay. All right, so now let me make another clarification to really indicate the following. So if we are looking at, let's say I'm going to look back at that earlier problem that I brought up when I was introducing about piecewise functions. So when we're looking back at this very first demonstrating piecewise function, how about the 3x minus 6 when x is less than or equal 5, okay, and then 1/2 x plus 3, okay, when x is greater than 5. Okay, so here's the thing. You see, sometimes when you write your own piecewise function, then you can see that if you see at least the 2 requirements here has our function breaks from a rule to a different rule depending on this value 5 right here. Because when it's less than or equal 5, then it's when it's less than or equal 5, then it's this rule, and when it's greater than 5, then it's this rule. But this, I just want to throw in this extra clarification for any of you who desire to learn the deep end of that. Okay, but see, when you write your own function, and something like this will be for sure an error. Okay, now if you have in your inequality, when you're writing up your piecewise function, think about in someday when you have your own interest to become a teacher, a professor, something like this is a serious typo over here. Either one of these two has to be a typo or an error, because here's the thing. Now, for something like this, then that means here's what the problem is. I mean, if we just simply read, then f of 5 f of 5. Okay, that means when x equals 5. But here's where the struggle comes in right here. When x equals 5 for that input, are we choosing this rule or are we choosing this rule? Because if both of these requirements include 5, then f of 5 equals 3 times 5 minus 6. And at the same time, this symbol technically or theoretically reads or logically reads and, but we switch. Okay, so this function equal to that if this requirement satisfied and can be equal to this if that requirement satisfied. But unfortunately, if the two requirements hasn't overlapped like this case right here, then when x equals 5, we have a battle. We have an arm wrestling situation here. That's which one do we choose? Okay, are we going with f of 5 equals 1/2 times 5 plus 3, or are we going with this? And this is where I'm saying it's an error, because doing this 3 times 5 is a 15 minus 6 is a positive 9, right? But then here it's a different value. It's a 5/2 plus 3 right there. Okay, and a 5/2 plus 3 is clearly a different value. Okay, so it's an 11/2. Okay, 5/2 plus 3 is an 11/2. So in the end, if this was the case, the reason I said out loud and I spelled it out loud was that this is an error when you're creating your function. Is simply because if you're choosing something like this, okay, then one input comes out with 2 possible outputs. This seriously violates the rule of it being a function. And that's why if we're writing something like this, it's just a sense about we have to keep checking our error and fine-tune our way of writing a piecewise function. Okay, anytime you're in a case where you need to write a piecewise function or check for someone's writing. So just like that, it's an error. But see, the following, as if you write things as the following is okay right here. So we're done with that case. Inequality cannot have equal signs in both pieces at the same breakpoint. Now, it's just an optional term right here, but this 5 right here, I call that a breakpoint or the break value for my students. A lot of time, because you see, we break from a piece to a different piece depending at that particular the value right there. But at the break point, if we have equal sign on both conditions around a break point right here, then that's an error. It's an error. Okay. But now, on the other hand, if we only use strict inequality, here's the break point. If both pieces use a strict inequality, the error, there's no error actually. Okay, but look at the difference between what I have just changed to now and what I wrote on the board earlier. On the board earlier, both of these inequalities have the equal signs, but here none of these inequalities have the equal sign. They're all strict inequalities. Okay, and so in that case, yes, we picked x equals 3. We have a clear indication of what to do. 3 is less than 5, and that break point right there. So 3 times 3 minus 6 in our understanding up to this point about piecewise function, and that gives me a positive 3. One input came out with one output. Now if I choose x equals 4.9 for example, okay, it's still we're gonna choose that piece because 4.9 is still less than 5. Okay, so 3 times 4.9 minus 6, and in this way we will definitely have a value other than the 3. Okay, and it's one exact unit, one exact value right there, and I'm a little hesitating to get this calculation done right there. Okay, and then when we go with 6, for example, then we know that we have to switch over to this other rule right here. That is going to be a 1/2 times 6 plus 3 right there. Okay, and then that now gives me, so it's a 3 order of operation. So 3 times plus 3 here gives me a 6. Okay, one input comes out with one output. So nothing wrong with any of these. And then with the way how we define our functions this way, our piecewise function this way, notice again, unlike the very beginning problem where I brought up, here there is no equal sign at all throughout the inequality. This is completely okay. Okay, because here, in that case, if we're asked to find f of 5, what do you think that answer will be? Take a moment to understand. Take a moment to think about that. All right, so here's my answer. It's undefined. Okay, so sometimes when you are having a piecewise function where the conditions are written like that, where there's no specific room, there is no specific room for this particular chosen input, because they are chosen input. So I mean, they are independent variables, so anyone can choose anything. So if we have no specific indication for what to do with this, with an input like that, then we have to say it's undefined, because there's no definition for what to do. There's no instruction from the function of what to do, when x equals 5. And so that's why it's formally stated as an undefined like that. All right, so those are some extra clarifications that I would like to make right there. Okay, and so now I was saying earlier, it is best to learn about this concept of piecewise function after you have learned about what a function is and be fluent to operate with a function using function notation. And so just like that, I also require that this lesson must be viewed after you have learned that any function has a graph. Because so here's my intention. We are now going to learn to graph. We're going to learn to graph a piecewise function. Okay, we're going to learn how to graph a piecewise function. So let me introduce the idea of what the graph of a piecewise function looks like first. Okay, so again, this is not a formal example yet. I'm going to bring back that earlier. So f of x equals, so how about, so there's that 3x minus 6 when x is less than or equal to 5. Let's bring back that original problem, that beginning problem where I demonstrated the idea. Okay, and then here it was a 1/2 x plus 3 when x is greater than 5. All right, let's look at the graph. Okay, let's look at the graph. So I am going to, so right now my only plan for now, when I'm introducing the idea, I just want to show the graph right on screen. So I'm going to use a software and you're going to see the graph popped out. Okay, and I'm going to explain how the graph is consistent with the understanding here. Okay, and then I will be putting up, after we have a clear understanding, then I will be putting up some examples where I will show you how we can graph it one by one in case we have to do the graphing manually. Because when it comes to graphing a piecewise function, either you have to have that skill to understand a given piecewise function from a graphing device, or you have to be able to make a hand sketch on your own right there for that. Because when it comes to manually doing the graph of a hand sketch, of a piecewise function, then a lot of times graphing devices are not doing a well done job right there. Even the software I'm using here takes a lot of time to program it before I can put it in here in our lecture right there. Okay, and so depending entirely on software is not always a good idea. So we need to learn how to be able to sketch our own, and then be able to learn how to understand a graph that's prepared by somebody else and given to us to see how it's consistent with the given piecewise function written here. Okay, so now I'm going to switch over to my graphing space. Okay, and so again, this is the function, that same function that I put it up earlier when I was demonstrating the idea of a piecewise function. Okay, so now in full view, full screen view again. Okay, so now I'm looking, this is the way how I see about the graph of a piecewise function. It has two pieces. Okay, so it has two pieces. So it makes sense that the graph must contain the picture of both pieces. The graph we're about to see must contain the picture of both pieces. Okay, so here, and let's bring in the pieces one by one. Okay, so along with introducing the graph, you will kind of start clicking into how we can actually do it when it's come to our turn to get the graph done manually. Okay, so the first piece is this function 3x minus 6. So what I recognize about this piece is that it's a linear function. This is 3x minus 6 is a linear function. Okay, so let's just tackle that down. Okay, so on that first piece right there, on that first piece, the function is that line right there. Okay, so how do I know it's a line? We should be fluent at this point because we have seen this kind of function in our previous course here. It's a linear function. So slope is 3 with y-intercept on the y-axis. We have a y-intercept at -6. And that's what you're seeing right here. So it slopes 3 is indicating that from the left to the right, our line is rising. Okay, and so in that way, this line for now at least looks consistent. That's all I'm saying. That's all I'm saying. This line right now looks consistent with whatever the rule that reads here. Okay, only focus on the rule for now. And then once we have looked at the rule, then here comes the next thing. But recall, our function is a piecewise function. Okay, so it's not only, I mean, this rule is not the only rule, but it's only, this rule is only valid, is only applicable when we have chosen an x value less than or equals less than or equal 5, less than or equal 5. Okay, so on the graph demonstration, allow me to do the following. I'm going to put in that line here. It's dotted because it's not meant to be, it's not intended to be part of the actual graph. It's just there because, see, this is where the breakpoint happens at. Okay, that's where the breakpoint happens at. And so now the condition says we want x's. We only want this line when it's x less than or equal 5. But see, as a big picture, where can we find x less than or equal 5? Or don't worry about the equal. You don't even need to worry about the equal, but where will it catch your attention when you're looking at the graph? Where will it catch your attention that x is less than 5? It's going to be to the left-hand side. It's going to be to the left-hand side of this vertical line because this vertical line is right at x equals 5. So less than 5, x is less than 5 means it's to the left. That now means I'm only going to pick, okay, and so I'm only going to pick that part of the line that's, all right, that's to the left-hand side of my dotted line right there. That's the whole reason. So now we have really the first piece successfully put down, okay, but now it's not quite complete yet, okay, because here's how I'm seeing it, What about right when x equals 5? Is x equals 5, is that specific input included in this piece? For this particular problem, yes it is. X equals 5 is included. That's why when I was teaching it, and you can kind of start seeing my thought process right there so that it will transform better into the work when we actually do a hand sketch ourselves right here. Okay, so the function is that piece. That's what explains for the line. But now we don't take the whole full line. We only take the line to the left of x equals 5 right there. And to the left simply because it's saying less than. So that's the big picture. What caught my attention is being on the left of 5. Okay? But now the question is, does it reach to equal 5? Yes, x equals 5 is included here in this requirement. So yes, it does. The graph will reach to x equals 5. Okay? So that means now my intention is to further say that now we have that endpoint here included as a solid point. Okay, so now I'm marking that solid point right there. All right. And so we got one piece now completely done. All right. So once we're done with one piece, let's turn our focus to the other piece. The other piece says 1/2 x plus 3 in that condition. So let's not be too worried about the condition yet. Focus on the shape of this function first. The graph or the shape of this particular piece first. Okay, so what we recognize here is another linear function. Slope 1/2, positive 1/2. Okay, and y-intercept 3. Okay, so every piece has its own kind of graph out there. Okay, that we just need to know. All right. So here we have learned from prior course, right? From prerequisite course that the 1/2 x plus 3 is a linear function. This is slope, and then there's the x and plus the y-intercept. Okay, and I'm not right now worrying about the condition x is greater than 5. So let me throw in that line, that reflector, that graph, that reflector, 1/2 x plus 3. Okay, so now back in full view mode right here. 1/2 x plus 3 is this graph. Okay, and again, do not worry about the graph here is intersecting with the other piece that we've had. The other piece is done. Let's leave it there. Now we're on our way to construct the second piece, which is this line that just popped out. Okay, so now with this line right here, once again, I only need anyone viewing this video to check for consistency. Okay, so if we dot a point, okay, if we pick a point, okay, think about there's a point right here, okay, and then there's another point on the line, and it should be at see, slope 1/2, or it's a slope 1/2 in a sense that we will have only one rise over two runs right here. One rise in one square grid rise over two square grids run. Okay, so it's consistent with the function, with the rule saying 1/2 x and plus 3. The line is still here. The y-intercept is also that point, being 1, 2, 3 at that grid, square grid 3 on the y-axis. So this line now is consistent with that rule 1/2 x plus 3. All right, but once again, once we've had the line completely drawn right there, once we have the line drawn down completely, the next question we're asking ourselves, and so everything I'm moving here is about this second piece. I'm done with the first piece. Okay, at some point I keep flashing back to recall your memory to get yourself on track and to be aware about the progress, where you're going. Okay, so now we got the first piece, but the question now, we got the second piece now, consistent with what the rule here is stating. But now we want to know, are we taking the entire complete line as indicated here, or are we only taking one zone of it? All right, so the answer here is clear. We are only taking one zone of it, because this function is switching to a line here, to this rule. And this line, you can see obviously is different with the other line that you have already seen. So this function is only equal to this line when x is greater than 5. Now we are blending in that requirement. So when x is greater than 5, as a big picture, it should be to the right hand side of this break line right here, of this breaking line right here, this breaking point right here. So here that dotted line is once again extremely important, because it's acting as my breaking point. Okay, and so now that means here right around that breaking point right here, I am going to disregard this part on the left. I'm only going to consider the line here to the right hand side, the part of this line that's to the right hand side of the break point right here, of the break line right there. Okay, and so now in that way, here's how I'm doing it. All right, and now that's how we're doing it. Okay, so now obviously the line only exists anywhere to the right hand side of this break point right there. Okay, all right, and I can adjust my viewing window a little bit. That's how we're seeing it. But that's not complete for our second piece, because again, now we need to look at that behavior right along with that dotted line right there, with that break point right here. Because see, so first thing, we get the picture of the piece, the complete picture of the piece, and then we take away the piece to reflect the requirements, and then we consider what's happening at the break point. Okay, are we including the break point, or are we excluding the break point? Okay, so in this case right here, our inequality is reading strictly greater than 5. That means we're only taking the portion of the graph that's completely to the right hand side of 5, but we're not including that break point. We are not including that break point. We are excluding the break point away from the inputs. So in that way, here's how I'm seeing it. Now again, back to full view screen right here. That is the break point, indicating that is the point, the end point at the break right there. Okay, and so it's indicated here as an empty point. Okay, for this, because anyone learning at this point knows and be aware and have already been aware that that we use an empty circle over here to indicate that we are not including this endpoint. And so now that completes our second piece of this piecewise function. So in the end, and now I can erase away that breakpoint. If you don't like that breakpoint, you can erase that away. Okay, but now it's all here. Okay, and this is our graph. This is the graph of this piecewise function. And so now it's even more clear. It explains even much further about why it's called a piecewise function, because now getting into graphing it, the function itself obviously breaks into two separate pieces. Now, the term piece makes people think something physical. There is your physical part that you can see right there. Okay, if you are not convinced that a rule right here is already a piece, a physical piece, okay, then we can leave that there. But now when we are looking at the graphic there, it has a visual, physical two pieces there. Okay, and that's why it's called piecewise function. Okay, so that graph right here is what is the graph for this particular piecewise function. Okay, and so in that way, let me bring in one more demonstration problem right here to see the graph and see how I demonstrate with the graph right there. And then we're going to start getting into an example where I show sort of like a live sketch. I mean, I'm not really going to do a hand sketch, but I'm going to use the software again. It took me a lot of time to program this on the software, but I'm trying to make it look like I'm graphing it with hands right there for you to understand the motion of it. But you already start seeing, I hope you already start seeing and clicking with some philosophy of how we graph these things. Okay? All right, so now... All right, so now let's look at another piecewise function. Let's look at another piecewise function. And so I'm going to put in, how about f of x equals, okay, and there's that curly braces right here, curly brace. And then how about a minus x plus 4. Plus 1, keep things simple. Okay, minus x plus 1, but for x being less than negative 2. Okay, and then we're looking at x squared, okay, for our values anywhere from negative 2, okay, and from negative 2 and 2. Okay. Then the last one here is a all right. So that's our complete. That's our piecewise function. 3 pieces involved here. Okay. And so my intention here is just to quickly show the graph. Okay, and with so much explanation from the earlier problem here, I'm going to start picking up pace here in this problem. And again, my only intention here is to show, to quickly pop out the graph and show how it's consistent. Each one of the pieces of the graph is consistent with how it's written here. Okay, and then after this, we are going to get into an actual example. All right, so in that way, let's have a look. 3 pieces. Okay, so let's look at the 3 pieces one by one. So you have seen that idea earlier. So on any piece, we get the complete graph first, and then we're going to start restricting it depending on the interval. Okay, depending on the requirements, the condition. All right, so in that way, here's my empty graphing space. Okay. All right, so this is the picture. This is the picture of the first piece. Okay, the complete picture of the first piece. Okay, so the first piece as a function, if it's a complete graph, then it's going to be a linear function, slope negative 1. Okay, and then with y-intercept 1. And that is why I see this line, as explained here in the graph. We have it's a slope, it's a negative slope, so it's from the left to the right, it's falling. Okay, and it has it's fall at 1 fall over 1 run. Okay, and then it has a y-intercept right at that value on the y-axis here, 1. Okay, and that is the reason that is consistent with this. Okay, but now I'm not going to take the full line. I'm only going to take, and so I have a break point. So it looks like minus 2 is one of my breakpoint right here. Okay, because switching between minus 2, okay, from this is the left hand side of minus 2, and then here is to the right hand side of minus 2. So minus 2 is one of the breakpoint. Let's put that in. Okay, so let's see. So there's the breakpoint minus 2. Okay, but the question now is, are we taking the complete graph here, or are we only taking one portion of that? We are only taking one portion of that. We're taking just to that part that's reflecting less than this negative 2 right here. So the negative 2 is on the left hand side in our picture. All right, so now I'm going to choose that part. Okay, now I'm going to choose that part where it's to the left hand side. So now that reflects how we have the graph here, but it's only strictly less than minus 2. So this dotted line is right at the breakpoint right there. Okay, but something is still not completed. Okay, something is still not completed, because you can see that the point is the pointer. What about right at the breakpoint right here? When x equals 2, when x equals negative 2, is x equals negative 2 included in this domain right here, in this zone right here? It's not. Okay, it's not included. So we're excluding x equals minus 2. So in that way, the point that happens right at the breakpoint, it needs to be an empty circle. So in other words, right here it has to be an empty circle. Okay, so now I am going to put that in. Okay, but it needs to be empty circle. All right, so now in a closer view right there, that's what my first piece looks like in a complete picture. Okay, and let's put that in closer, complete full view screen right there, so anyone can have a better view of that. All right, and so now that's the first piece. And then let's look at the second piece. The second piece now is when x is passing to the right hand side of minus 2, that breakpoint with that dotted black line right there. So now when x is anywhere in between this interval, okay, between minus 2 and 2 right there. But then let's not too worry about this interval. The second piece as a complete graph, it's the graph of this x square function. X square function is among the toolkit functions. So at this point, feel free to pause the video and search back at my earlier videos, so that I talked about I instantly brought up the graph of this particular piecewise function. You must have seen it. Okay, and so now allow me to assume that you have already paused the video and have a reminder about what the graph of that piece of that the toolkit function is. And so now on my screen right here, this is the graph of that x square function. In complete view. In complete view, the x square function graph looks as following. It's this cup right here. All right, and so now once again, you can always pause the video and look at this graph here, that nice parabolic shape right there, and compare with what you have seen earlier, that what I was calling the graph of the toolkit function x squared, f of x equals x squared. That is this one right here. So it's just another verification. Okay, so that now that you've had the complete graph of that x squared function, the graph of that toolkit function, the question that we're putting, the question that we have, the next question that we have for ourselves, are we taking the complete graph of this toolkit function x squared, or are we only taking that in some zone of values? The answer to that question is here. We're only taking the graph that's in this zone of input values x. Okay, and so now this zone is happening anywhere from negative 2 to less than 2. But so now notice we have a second breakpoint. So negative 2 was already explained to be a one breakpoint, but I'm going to have another. It looks like we're going to have another breakpoint right here, a break line like that. All right, and so now in that way, here's the second break line right there. So now this is x equals negative 2. This is x equals 2. Okay, and so the graph is only happening in between here. The graph should be only happening in between here, not outside to the left, not outside to the right. So the zone that we see this graph, the zone that we visibly see this parabola is only in between -2 and 2. Okay, so that's the logic of that. So now let's head down to that. Okay, and so now this is what reflects that the part of the graph, the piece of the graph that we're looking at for the Toolkit function x squared now is consistent with this zone requirement. We only want the shape to be this parabolic shape inside of that zone, anywhere from -2 to 2. Okay, but that did not complete our graph yet, because we need to ask ourselves the next question. Okay, what about the two endpoints? Are we including both endpoints, or we are excluding one of them, or we are excluding both of them? Okay, and so now we need to read even further into this inequality, this three-sided inequality. What it says here is that x can equal -2, but x can't equal 2. Okay, so that means it's included. X equals -2 is included with this graph as a solid point, but x cannot equal -2. I mean, x cannot equal 2, or x equals 2 is excluded from this graph like that. Okay, so on the right end here, it has to be an empty point. All right, so now on the graph like that. So on that left end, it has to be a solid point, as I have explained earlier. Okay, because x equals 2 is included as part of this graph. Okay, but now when x equals -2 is included as part of this graph. Okay, but x equals 2 is excluded. It's not included here. So I'm going to put the point there, but I have to leave that as an empty circle. All right, so now we have empty circle there. Okay, and so now that completes our graph of the second piece. Okay, that completes the graph of the second piece. And then let's now move on to the third piece. Okay, and the picture is still there. Let's look at the third piece. The third piece here seems like a constant function. And so this constant function right here is also one among the Toolkit function. The constant here is 4. So according to what we have seen with the constant function, the graph is just a one flat horizontal line graph right here, being as high as 4. Okay, so let's look at that. So as far as the complete graph. All right, so here's the graph of the third piece right here as a complete graph. All right, so the graph of this complete function right here, this is namely f of x equals 4 right here. Okay, so at every x value we are at height 4. That's what this horizontal flat line is at. Okay, so now that we've had the complete graph for this third piece, but again, we're not going to pick the whole, we're not going to use the entire graph like that. We're only going to pick this graph right here when x is greater than or equals 2. Okay, greater than or equal 2. That means we're now at least what caught my attention is it's to the right hand side of that breakpoint. Okay, and the breakpoint is at that dotted line x equals 2. All right, so now let's look at that. So in closer view, the x equals 2 line is right here. So as I argued earlier, we only want to the right hand side of that. So now I'm gonna, all right, so now I'm gonna complete out my graph. Okay, so I will take only the part to the right hand side. So that means that's what it looks like. Okay, that's what it looks like. So now everything to the left hand side of that flat line is taken away, because we don't need that part. We only need to see that it's only consistent where to be this horizontal line when it's x greater than or equals 2. So at what the bigger part that caught my attention is to the right hand side. Okay, to the right hand side of that breakpoint. And then now the next question we're asking ourselves, are we including or excluding that endpoint right on the break line right there, right on that break line, the vertical break line right here? Okay, and so the inequality here says, x greater than or equal, That means we do include x equals 2 in this graph, in this line right there. All right, so now I'm swinging back to my browser in full screen view right here. So this point is indeed filling in for this line right there. So now that particular point, okay, I will bring it up and as a solid point. Okay, so here's the logic right here. In the middle piece, it was an empty point, but this piece right here comes in with a solid point. It's filling in right there. So in the end, that point right there also has it's just like a continuous point that's going through right there. All right, but now this is the graph. Okay, this is the graph of our particular function here, this piecewise function. And once again, it demonstrates the idea of why we're calling that a piecewise function, because it's broken into 3 pieces. We are seeing 3 separate pieces of graph on this particular picture right here. Okay, and so that's how the graph, and my only intention is to show how the graph is consistent, appears to be consistent with what's written here. So you can take that skill to prepare for your own kind of problems out there, where people just simply hand you a graph and hand you a set of piecewise function and make you match. For example, hey, which one of the graphs here is matching with this is the correct graph, okay, of a given piecewise function. And then that's the skill you've learned through this demonstration. Will be the skill that you use to pick your right choice or the right match for the graph that matches with your the piecewise function. A lot of times we're doing problems like that. All right, but now let's get into an actual example. Okay, an actual example where we are gonna really do one problem from really. I use computer software, but I'm gonna really make it look like I'm gonna really draw it. Okay, I'm gonna really draw it. All right. So now let's look into sketching an actual graph of a piecewise function. All right, so now in what I have right here, all right, so from my notes that I have prepared, let's now look at example 2 right here. Okay. And so in this one example, I'm actually going to show the hand sketch version for 2 separate piecewise functions. So let's graph each of the following. Let's graph each of the following piecewise functions. Okay, and that's the requirement. That's the wording instruction of this particular example. Okay, so now here comes part A right here. So how about we want to graph this function right here? F of x equals okay, and I will be looking at about minus 2x plus 3, okay, for x is less than or equal -1. Okay, and then we're looking here at 2 for x greater than -1. All right, so that's the problem that we want to do a hand sketch on right there. Okay, and so now for this function right here, well, it's 2 pieces, piecewise function, 2 pieces, right? And so just like that philosophy, that fundamental that I was demonstrating earlier, okay, but this time I'm gonna, now again, I'm saying technically this is a hand sketch graph, but I'm just using a software to make it look like I'm doing an actual hand sketch graph, because in the end I'm not feeling confident. I don't believe in my own sketching skill right there. Okay, but then the whole point, the whole purpose of this example is that there are actually no, I mean, the reason I have to show you how to do that as a hand sketch, as a manual sketch right here, because there are no software that will, hey, here you go, one piecewise function, boom, get the graph. That even your TI calculator, it's gonna take a lot to get a piecewise function done. Okay, and so the decimals I'm using, it took me a lot of time to prepare. Okay, so that's why be able to make a manual sketch of a piecewise function is a good idea in times like this. Okay, otherwise it's gonna have to be a separate lessons where I show you, if there are 10 technologies out there, I'll have to make a separate lessons showing how to graph these piecewise functions for 10 separate technologies. So here I'm only using technology to describe what my hand motion is doing. Okay, if I was doing it as a hand sketch, that's all. Okay, but in the end, my main philosophy, the main aim for anyone viewing this video is you think about you're drawing this as a hand sketch, as an actual manual hand sketch right there. So have graph paper ready and papers and pencil, and pencil and erasers. Okay, straight edge is also an excellent addition to that, but in these modern days, not many students are patient enough to use a straight edge or kind of ruler. Okay, but now in that fundamental that I pointed out earlier, we're gonna sketch the graphs here one piece by one. So one by one and by one in its order. It doesn't hurt to go from top down. Okay, so we're gonna sketch the idea is that we're gonna sketch the complete graph first based on our understanding of the current piece. We're gonna just simply sketch on each piece. We start out sketching the entire graph first based on our previous understanding about the function in that piece. Okay, and then after that we're gonna restrict it down to the zone. Okay, so let's get it done piece by piece right here. So all right, so now in my graphing space, okay, with this graphing space right here. All right, the first function is a linear function. -2 is the slope, so 4/2 over 1 run, and then it has a y-intercept right here. So knowing that this is a linear function, we have learned this from previous course. If we were doing this manually, then I would always, at least this is the way how I taught my students in the previous course right there, about how anytime when you graph a linear function in this slope-intercept form right here, then I taught my students to start out drawing this, and you can have your own way of doing that, but what I'm doing here is it reflects how I would teach, you know, a student in my previous course how to graph a linear function in slope-intercept form. I'm going to start out right with the y-intercept right here. So on the y-intercept, with the y-intercept being +3, that means right on my y-axis here, right on my y-axis. Okay, I'm going to put that y-intercept in there. Okay, so there you go. That's my point. And I'm talking about right now, the philosophy is I'm just trying my way with my understanding to get the complete graph of this first one. And that's why it brings back all that skills that you got to know how to graph linear function and how to graph a constant function and all that. So I'm on my way of sketching this linear function. So I'm using that y-intercept being 3 right there. And then from there, it's going to be 2 fours. That's why I'm dropping down 2 square grids right here over 1 run. Okay, so about there I'm going to dot another point. Okay, so over 1 run and 2 fours. That's why another point. And now I can draw a line through this. So see, my mouse cursor is going to indicating the direction that I will be sketching. So I will use, and thankfully I have this software, so it makes a straight line going through. But that's the point. The straight line is to be sketched through these 2 points. All right. So in that way, now I'm going to make my sketch right here. All right, so let's slowly get it. See, so if I was using a pencil tip or with a straight edge, then I'm going to be making a graph like that, okay? And so you can see that it's moving from the left to the right. All right, so because if I was putting a straight edge on there, it's going to be drawn just like that. And so you saw the motion of how the line was changing, and that's the idea. So the pencil tip was moving in this way, connecting through. All right, so now that we've had the line, And then now we completed that line, but the question we're asking ourselves next, are we staying with the complete line like this, or are we only taking a portion of that? Okay, and so now the requirement says this function is only going to equal this linear piece if x is less than or equals -1. So it looks like we have a breakpoint here at -1, x equals -1. So if that would be me graphing it, I will draw in that with straight edge, of course. That will help a lot. Okay, so I will put in a vertical dotted line. So we can easily, and this thing here is easily at -1. All right, so that straight edge here is at -1. So now apparently we're not going to take, according to the requirements of this piecewise function, we're not going to take values above -1. We only take values less than or equal -1. That means on the graph here, in the way how I see it, should be only to the left hand side. It should be only to the left hand side. So now if I was doing it, I'm going to think about using eraser to erase away this part right here. I'm going to erase completely everything to the right hand side of this vertical line, x equals -1, because that's all we need. We only need this left hand side. Okay, so that's the idea. So in that way, here's how I'm going to be doing it. All right, so erasing away this part right here leaves behind just that. And also I'm going to erase these 2 points that I used to draw my line, because the 2 points I put there only helped me to draw the line. But now once I got the line done, and if it happens to be outside of my area of the line that I need to take, I'll just erase that, because everything of the line that I need is right now right here to the left hand side of that break line right there, that breakpoint line right there. Okay, and so now once we have erased away the breakpoint, I mean the part that's to the right hand side of the break line point, and we only keep this left hand side. The next question, again, just like the fundamental you have seen in the demonstration problem, are we taking the endpoint here at x equals -1, at x equals -1? Are we taking the endpoint there, or we are excluding it? Okay, are we including x equals -1 in this piece of the graph, or are we excluding it? Okay, so the answer here, according to this inequality, we are including it. We are taking it. Okay, we're including it. So that means it's going to have to be a solid point. So now with papers and pencil, I mean with simply a pencil, we can just simply put a solid point right there. Okay, and so solid point, and that point right there right now, because I'm unsure, but it has to be some point there. So now I'm gonna change that to a solid point. Okay, so that's the idea right there. So now at least I know that I have completed my first piece of this piecewise function. That's how it's done. Okay, and then once we've got the first piece completed out, let's move on to the second piece right here. Okay, so once again, we're gonna repeat the process. We're gonna start out by just simply making a hand sketch of the complete graph using our own understanding about this kind of function. So from our past understanding, this is a constant function. So when we're sketching it, it has to be a horizontal line. Okay, and it's a horizontal line that's passing through the y-axis at y equals 2. Okay, so I'm saying out loud, I'm verbalizing out loud those information. So here's how I'm doing it. Y equals 2 is about here on the y-axis. Okay, so that means now I am going to put that, because I know that my line is going to be a horizontal line going through right there. So I'm going to put, and it's being that high, it's a horizontal line, so I'm going to put that first point being right on the y-axis. It makes sense that how we draw it that way. Okay, and then I'm going to use a pencil to put another point here. Okay, to put another point here, because we know that our line will be a horizontal flat line. Okay, so I'm using the 2 points right here just to show that anytime we're drawing a line, we need 2 points, and then we use a straight edge to connect through the 2 points. Okay, and so now I'm going to draw a line with a straight edge right through those 2 points. Okay, so here's how my line looks. All right, so let's draw that. All right, so now That demonstrates that I have just now used a pencil to draw a line through that's passing through these 2 points there. Okay, and so now we got the line, and it's a horizontal line. It's consistent with this rule over here. Regardless of what that input is, the function is a constant value. F of x equals 2. Okay, or y constantly remains 2. The output constantly remains 2, regardless of what x value that is. Okay, so that's the complete graph. But now again, once you've got the complete graph that describes this second rule over here, this curtain rule that we're at right here, then the next question we're asking ourselves, are we taking the complete graph like that, or are we only taking a portion of it? Okay, and the answer now is we're only taking a portion of it. Okay, so which portion then? It's this portion that reflects, that represents x greater than -1. Okay, so again, that breakpoint is at -1. We have that breakpoint right here represented as that dotted line, that dotted vertical line. So now in closer view, being greater than -1 means I'm only going to take this part that's strictly to the right-hand side, strictly to the right-hand side of -1. All right, so here we go. That means what's going to happen to this part to the left? We're going to completely erase that. Okay, so in that way, now I'm going to erase away the part that we don't need. That's how it happens. Okay, and erasing these two points away or not, that's pretty much your choice right there, because it's in the end it's still part of the graph, so it's actually a good idea to still leave it here. Okay, but now once you've had the line, okay, then what about the endpoint right here? There must be something with the endpoint, and right now I'm not sure what that behavior is. I just put that as a quick little cross point right there, and then we're going to decide. Okay, so right now a little cross right there is to indicate that there will be some endpoint behavior right there that we're going to have to consider carefully. So now let's look back at the requirements here. Are we including x equals -1 or not? Okay, and at that point the answer is clear. We are not including x equals -1 in this piece right there. So that means x equals 1 is not included with this piece, or in other words, that point right now as an x, as a cross right there, that point right now. And see, if you are using a pencil, it never hurt to use a cross right there and another cross right there, and then once you are firm about the actual, whether it's solid or empty point, you can just fill it in. Okay, and so now back on that endpoint that I'm drawing as a cross right there, as a quick little cross right there. Now it needs to be switched to an empty point, because we know that we're not including that endpoint right there. But now, and yes, I can gently erase away these 2 points, even though I know they're on the line, but the point is making it a little too big like that. But now that fine-tunes our graph and completes our graph like that. Okay, and that is the graph for this particular piecewise function. Okay, it's broken into 2 pieces. You are now seeing 2 pieces of graph like that in front of you. Okay, and it reflects everything that's being described here. All right. And so now let's look at another problem where again we're going to be graphing another piecewise function. Okay, and I can start picking up pace a little bit more, and then I'm going to grow the problem a little more challenging, more pieces involved. How's that? Okay, so all right, so how about here? Let's look at the function f of x equals, and as far as the piecewise right here, let's look at x squared for x less than or equals 1 All right, so here comes our piecewise function that has 3 pieces. Okay, and we are going to, with papers and pencil, we're going to graph this. Okay, all right, so you can pause the video to take note of the function if you're learning along with this video lesson right here. And I'm going to swing by my computer screen to get my graphing device ready. All right, and so now, once you have had enough time to pause the video and copy down the notes, we are looking at all right, so after spending some time preparing the screen, okay, and here's how we are ready for the work right here. All right, so just like how I was doing that with part A earlier. So now we're going to draw the first piece. The first piece here is this x squared function. Okay, it's one among the toolkit functions. So at this point, constantly review your toolkit function. They are called the toolkit functions because now, according to the book that I'm mostly using, okay, to create my the lecture notes right here. So this function here is among the toolkit function. And they are called the toolkit functions because see, you can use them anywhere in any problem and know them because you can see how handy they are. Okay, and so now being an x squared function, then I can graph my x squared function as following. Usually with just 3 little points like this, okay? Then I can draw my x squared function as a quadratic. All right, so from the left to the right. All right, so that's how it works. So let me slow down my action a little bit more. So think about undoing this, okay? And all right, so now slowing it down a little bit, okay? And that's the graph of my x squared function. Okay? But now the question is this graph, are we taking this graph as a complete graph, or are we only taking one portion of that? Okay? And so now, just like that, just like how we have done the earlier problem, so now we have a breakpoint at x equals 1 right here. At x equals 1. So imagine if we have paper and pencil, a piece of paper and pencil. I'm going to just draw in that vertical line that represents x equals 1 as a breakpoint right there. Okay, so now in full screen view right here, x equals 1 is this line. Okay, and so now we are only taking the portion of the graph. We're only taking the portion of the graph that is to the left-hand side of 1 because the inequality is reading right here. This function is only behaving as a is only behaving as a parabola. This graph is only a parabola for x anywhere on the left-hand side. Anywhere on the left-hand side of x equals 1, and x equals 1 is that vertical line. So that means as an impact, I am going to erase everything to the right-hand side of x equals 1 and only retain the part that's to the left. Okay, and so now back on the graph. All right, I'm going to keep only the parts that stays to the left-hand side, just like that. Okay, and then right now leaving that point there is a little too rushed, so I'm also going to put that point away. Okay, because we don't know if it's included or not. Okay, these 2 points were just for drawing, these 3 points were initially for drawing a parabola, but now I have to erase that point to consider that a little more carefully. Okay, and then to fine-tune the graph, I can just also lightly erase away those other 2 points. So now that's that portion of the parabola to the left-hand side of x equals 1. But now, what about the endpoint? So right now I put that as a cross because I'm unsure. I'm not sure whether it's an included point or an excluded endpoint. Okay, so we're going to have to take a look. So the inequality says x equal 1. That means we can let x equals 1 and substitute x equals 1 into this rule right there. And we have seen that in the earlier example where we basically evaluate a piecewise function at different various input values. And so now x equals 1 is included with this. So that means we're going to have a solid point right on that vertical breakpoint line right there. Okay, so now that means this point right now drawn as a cross right here. Now I'm going to switch that to an actual solid point. Okay, so that completes one piece of our function. Okay, that's complete one piece of our piecewise function. Let's now move on to the next piece. And so we have had experience with this function, with this kind of function before in earlier example. It's a constant function. So flat horizontal line is expected. Okay, so now again, first thing is just to, as a hand sketch, just draw the complete graph first. If we just simply draw that only one function. So this function is a horizontal line at y equals 3. Okay, so I'm going to use, I'm going to put one point right on the y-axis, just like that. If we're doing that with paper and pencil, that's how it works. And I'm going to put another line at the same exact height. Another point at the same exact height. And I'm going to draw a line through. Okay, and so all right. Now let's draw a line through. All right, so here's our line right here. All right, so that's how I'm drawing that line through as a horizontal line right there. Okay, but now once we have completed, so that's the complete graph of our, if it was f of x equals 3. But now are we taking the complete graph or are we only taking a portion of it, a part of it? Then now we're going to need to look it up in our restriction right here. It says we only take the part where it's anywhere, well for now it's easier to read, anywhere between 1 and 5. Let's read it that way, anywhere greater than 1 and less than 5. And then we will consider endpoints equal signs later. Okay, so anywhere between 1 and 5. All right, so in that way, and I mentioned earlier, 1 was already considered as a breakpoint, and now we realize there's another breakpoint right here. Okay, and so now in complete full view right here, x equals 1 is here. That's one breakpoint. Well, we have another breakpoint right at x equals 5. So I'm going to need to put that in, okay, with a straight edge. All right, and so now that's how I put in the other one. Okay, so there's that other straight edge right there. Okay, and so now, this is the other breakpoint. So now we only take this line, this horizontal line only exists in between that. Okay, it only exists in between that because of that inequality. Okay, so now I'm gonna erase everything that's outside of that zone. All right, so in this picture, everything that's in this zone and everything that's in this zone, I'm gonna erase out. Okay, so now that means all of that is erased away. Okay, and now I'm also going to, because that drawing points, that guiding points to draw my graph, these points right here, we're not sure, this point here is obviously outside of the zone we need, so I'm going to put that point away. Okay, I'm going to delete that point out. Okay, and this point right now, it could be part of the graph or it could be not, so I'm also going to take that out and we're going to consider that later. Okay, so now the two endpoints here, now I'm going to start out with the cross signs here, because right now at this moment I'm not sure whether we're including these endpoints or we're excluding both, or we are including only one of them. Okay, and so in that way, after you see the hand action, and now I'm gonna look back at the inequality. The inequality says we can have x equal to as low as 1. And now I just realized I've made another error right here. Okay, this inequality was a typo from the beginning, that it shouldn't have that equal sign right there. So now in this inequality, I'm looking at x should be strictly greater than. So it was an error I've had here. Okay, x should be strictly greater than. So we are not including x equals 1. Okay, we're not including x equals 1 in this line. So that left endpoint there, that cross sign right now, right on that line, x equals 1 is not going to be included. It's excluded. But then it will be included. This right endpoint will be included. Okay, on the other breakpoint like that. And so now we have a clear direction. All right, so this left endpoint is now switched to a solid, an empty point because it's not included. Okay, and then this other point now is clear that we need to include that. So I'm going to switch that to an actual solid point. All right, so that's empty point, that's solid point. Okay, and so I had to, I need to apologize, viewers, for making about 2 errors today. But see, that's a lot of time. It happens a lot with professors too. And that's why I showed that technique for earlier. Sometimes when you write your own function, because that happens to me quite a few times as well in my career. That a lot of time when I write functions, and especially when I'm writing a function improvised, then it's easy to make those little mistakes. Okay, so here, since I already chose equal 1 here, then we can't have that equal 1 again here. All right, but anyway, so this is the correct version of that. So now we're done with the second piece. Okay, and let's move on to the next piece. And so before we're moving on, let's check. This is all free of typo over here. Okay, because there's equal sign here was accepted that way, and so this one here must come without equal sign. Now, both without equal signs is okay, but both with equal signs is not okay. All right, and so now we double check, and that's good for here. So now I'm ready to put in the third piece. Okay, but now as the usual procedure, I'm going to go ahead and sketch the complete line here first. Okay, all right, so on my graph, for the third piece, all right, it's a line again. It's a line function, minus x plus 6, minus x plus 6. It's a linear function. It's a line function. Slope -1, falling down slope, and then at y-intercept 6 on the y-axis. Okay, and so now just in that way of understanding, now I'm going to write on my y-intercept right here. I'm going to put, right on my y-axis, I'm going to put, okay, x equals, I'm going to put y equals 6 right on my y-axis. This is only I call a guiding point to help me draw my line right here. And from here, I'm going to go, with slope -1, I'm going to go 1 over and 1 down. Okay, that's how I got this second point. Now I'm going to draw a sketch over that. Okay, I'm going to sketch a line through that. Okay, so now here's how the sketch happens. All right, let's sketch it. All right, so I hope that animation right there was showing that if I was using a pencil, I'm going to sketch it like that. Okay, and so now this is my complete line for now. This is my complete line for now. But with this third line, the question again is, am I taking the whole complete line? Obviously not, because it's interfering with the other parts of the graph, right? And so we're going to only take that line minus x plus 6 for anywhere x is greater than 5. So that breakpoint line is right here. That breakpoint line is at x equals 5 already in dotted line. So we only interested in the part of the line that's to the right hand side, the part of this red line right here, that's to the right hand side, of this vertical breakpoint line right here. So that means I am going to, okay, erase out everything to the left of that break line point, and that's how it happens. So it just disappeared to indicate that I erased that line, that part of the line to the left hand side of x equals 5. Okay, and of course now I'm unsure about the end point. I'm going to leave that as a cross like that. Okay, and now I don't need these points right here, because leaving too many details in your graph brings no good other than just confusing the viewers. So I'm going to take those points out, and of course I only use them to sketch the graph, but in the end they are not part of that third piece of the graph, and so it makes sense that we are taking them out. We're clearing out these 2 points right there. Okay, and so in that way, yes, let's take them out. Okay, so now this point right here, currently in as a cross symbol, because we're not sure whether we're including that point or we're not. Okay, so now let's have a look. So it says the inequality says I want greater than 5. Okay, I want greater than 5, and the inequality goes strict inequality, strictly greater than 5. So that means it's not included. This endpoint is not included with this line right here. So right on that cross right there, it has to be switched over to an empty point, an empty circle. All right, and so now on my graph in complete full view, full screen view right here. Now I'm going to switch that point to an empty point. But that has now completed our graph. And at this point, you can erase away the 2 vertical lines right here, because they're not really part of the graph. They're just there to help us drawing. So now if you don't feel it's too much, you can erase those too. And that now completes the graph of our piecewise function. 3 pieces. This is the x squared piece. This is the constant piece, and this is the minus x plus 6 piece right here. And that's the graph for this particular function in our part B right there. All right.